Planets.
Galaxies.
Black holes.
Quasars.
Supernovas.
Starburst galaxies.
Clouds of gas and dust.
The Milky Way.
Solar magnetic fields.
Exoplanets.
Dwarf stars.
Pulsars.
Gravity.
Active galactic nuclei.
Dark matter.
Gravitational
Dark
waves.
energy.
Helioseismology.
Stellar evolution.
Moon. Inflation.
Electrons.
Solar cycle.
Super Jupiters.
Neutrons.
Galaxy.
Dwarf galaxies.
One of the things that makes us human is our curiosity.
We're a curious species. We want to know what's out there and how did it get to be there.
Since antiquity, we have been trying to find as humans our place in the universe.
It's only been in the last 100 years or so that we've known that the sun is not the center of the universe, and that the Milky Way is not the only galaxy in the universe. There are hundreds of billions of other galaxies in just the observable universe.
The more we understand, the more detailed questions we have.
Today, astronomy is asking big questions, fundamental questions on the largest scale, like
How did the universe begin?
What is the universe made of?
How do stars form?
How do galaxies form?
How do planets form?
Is there life out there?
What's the kind of universe we live in?
Are we alone?
what is the map of our universe if you could zoom out to the largest scale?
Are we just one universe in a multiverse?
So we're still grappling with really fundamental questions at all these levels.
That's been the whole purpose of physics and astronomy throughout history, is to come up with a better and better explanation of how the universe works.
Scientists observe nature. That's our job. We observe nature and we interpret it. And for astronomers, the part we look at is in the sky.
The universe started with a Big Bang.
The Big Bang is the beginning of space and time. We think it's a singularity when all of space and time and all the matter and energy in the universe was in one place. After the Big Bang, there was the evolution of the universe, the evolution of heavy elements, the evolution of the Milky Way that eventually led to the conditions on Earth that were favorable for life and complex life and then intelligent life. And now we're at a stage where the universe itself, we're part of the universe, can look at the universe and contemplate itself and contemplate the beginning and structure of the universe.
In astronomy, you kind of can't help always thinking about the big picture, how it all fits in.
Yale has a long legacy of being a major player in astronomy since the 19th century. Building on that legacy, we now have a new generation of people, all of us in the department now, who are continuing to push at all the new frontiers.
One of the neat things about the Yale Astronomy Department is just how many individual research groups there are and the variety of research that's done.
We have people who study the stars. We have people who study the planets that go around them.
We have people studying large galaxies and small galaxies and cosmology. We have people who focus on the observational aspects. We have people who do computational. We have people who do almost pure theory.
And so astronomers study all these aspects, but since they are all connected, often people study multiple things at the same time. And often breakthroughs arise when faculty who study different areas work together and then find completely new directions of research that combine these different expertise.
We all want clarity in what we're studying. We want a deep level of understanding. And so we are open to learning from each other.
Three-dimensional shape.
So this is the no subpanel evolution.
This is a mechanism before. Every day, there's an opportunity to talk about advancements that are happening today in the field. There's a stellar tea where people get together and talk about all of the important papers that are being written about stars. There's another one that happens where people get together and talk about all the important papers that came out that week that have to do with galaxy evolution.
The center of inside the circle.
we're able to invite researchers and professors, experts from across the nation to come in, or to host workshops and conferences on campus.
These are the other visual components in the merger.
I think the most amazing thing about the Yale Astronomy Department is how much it's changed in the last decade.
We made a huge leap forward about 7 years ago now when we joined the Keck Consortium and got observing time on the Keck facilities in Mauna Kea in Hawaii.
The big discoveries in astronomy always come when you get to take a new look at the sky, and that means having new technology, new telescopes, looking at things in different ways or asking different questions.
Astronomers have always wanted to build bigger telescopes, because the larger your telescope is, the more light you get. And that means that you can't just see more of the universe, but you can also look further back in time. The Keck Telescopes in Hawaii are the pinnacle of this evolution in telescope building. And at the moment, they offer the best opportunities for astronomers to study the universe, to see things as they were only a few billion years after the Big Bang.
When you're studying the universe, you want to use all the information you possibly can.
We're starting to get to the point where we're now starting to get time information, so we can just watch how the universe evolves with time. And all of that is just a huge amount of data that we can go back to and ask very detailed questions of.
The way in which computers have changed over the last 5 years or even the last 2 years has opened up some pretty incredible avenues of astronomical research in terms of running simulations, comparing data of different kinds. With all of this data that's available to us, we can actually make statements about the average properties of things that are really statistically robust.
So it's really, I think, the power of astronomy, especially today, is that we're at a point where we can take observations, an actual census of the sky, and combine that with theoretical models and predictions from mathematical and physical theories to get an idea of what our actual universe looks like.
One of the things we've learned is that the universe is much stranger than we had ever imagined.
Invisible entities appear to be the most powerful entities that are shaping the universe.
Dark matter, dark energy, black holes.
When I was in high school and college, we barely knew black holes existed. I mean, they were a prediction of Einstein's theory, if you like, but nobody thought they actually existed in nature. And then astronomers discovered objects that could only be explained simply as black holes. They're dense concentrations of matter where so much matter is stuffed into such a small volume that no particles or even light can have enough energy to escape the black hole. But because they're a big mass in a small volume, matter tries to fall toward the black hole. And in doing so, it heats up and glows. And in fact, the regions outside black holes are very, very luminous.
Dark matter is something that has mass, and we see its gravitational effects. For example, the Milky Way is rotating too fast. If the Milky Way were only held together by the visible mass that we see in the form of stars and gas, dust, things like that, the Milky Way would fly apart. But it doesn't, so there must be some extra mass there that's gravitationally pulling the matter into orbits around the center of mass of the Milky Way. That's how we first discovered the dark matter. Now, dark energy and dark matter combined make up 97% or more of the energy and mass of the universe. And we don't know what it is. There are various theories, but we don't really know exactly.
But what we now know are that these entities are important in the universe. They shape the universe. We know how they're distributed. We know how they function. We don't know what they are. Their nature remains elusive. The fate of the universe, the geometry of the universe, and the contents of the universe are completely interlinked. What M actually does is it...
I decided to come to Yale because of the ethos. It has this collaborative, creative, energetic, young ethos that, as far as I can tell, is entirely unique. And it allows this kind of science to happen that is entirely different than anywhere else that I've experienced. And it's really exciting.
When you show up at Yale, you don't just sit in a classroom. The big push the minute you arrive is to do research. It's the best way to learn this work, is to take data, see what it means, interpret it, write about it. And practicing that process is extremely important. In a way, when you begin as a graduate student, you are an apprentice. You're an apprentice to a faculty member who is teaching you their craft.
Rotation, uncertainty, turbulence correction.
Clearly we're scaling with surface brightness so that, you have to go to very low.
I think this is nice to go through for us to understand it.
Yale is really good at asking the hard questions, at saying, where are these areas that are nebulous? Where's the most uncertainty? And that's where we go after first, because the hard questions are the ones with the coolest answers, with the best results, the things that I think propel the field forward.
For such a high-intensity research university, Yale is incredibly undergraduate focused.
Undergraduates are really seen as part of the department.
Yale undergraduates have an enormous opportunity to do research with faculty. Every single group in our department has at least one, if not more, undergraduates who have not only done research, but have done productive research leading to first author papers.
The students, the undergrads especially, are always great at bringing questions. Sometimes they really are questioning whether or not we're on the right track. And this forces all of us to sharpen our thinking and not to just skip over or gloss over something, which could actually make the difference between success and failure.
Part of our success with undergrads in research comes from our coursework. I teach a class called Research Methods. It's specifically targeted at sophomores to teach them all the skills they need to be useful in our research groups, and also how to think like a scientist. As an introduction, students are looking at neon tubes. This is tubes of gas that have electricity pulsing through it. The elements in that gas produce various different spectral lines. And in fact, the lines that we're seeing in these spectral tubes are identical to what we see astrophysically.
When you want to really understand the objects, you have to spread their light out in wavelengths and look for characteristic signatures that are due to the atoms in that object. That's how we tell what stars are made of, what temperature they are, etc.
This allows us to determine if the star is moving towards us or away from us. That in turn can tell us if the star is being orbited by planets. This is one of the main ways that we detect planets around other stars.
Almost every star forms with a planetary system. And it's by watching the wobble of the stars that we actually detect the unseen planets around those stars. In about 2007, it became clear to me that the field of exoplanets was not going to progress unless we built better instruments. So I put together a team, and the mantra to the team is, we're not doing the same thing that's been done before. We're going to break into new ground and push the limits of science. So we're doing that at Yale. We've made some incredible breakthroughs. We're now building a spectrograph, which I think will have unprecedented precision. We're trying to move to the next level. What's at stake is who's going to find the Earth version 2.0 orbiting nearby stars.
Astronomy is one of those fields in science that is completely accessible right away. So you don't have to know everything about astronomy to find that awe and wonder.
Here at Yale, we're fortunate to have a fantastic education and outreach center, the Leitner Family Observatory and Planetarium. The Leitner Observatory and Planetarium has several important roles in fulfilling the mission of the department and the university. One of the most important roles is for undergraduate education, for teaching. Every clear night we'll have classes coming up to do various experiments with the telescopes. They can make direct observations of stars and galaxies and nebulae, and they can actually see these things for themselves. We also use this facility as a way of giving our students teaching experience. The graduate students will come up and volunteer on public nights. It's amazing the first time you see Saturn through a telescope, or the first time you see a beautiful star cluster, or the Orion Nebula. Every middle school kid should have the chance to go look at Saturn through a telescope and be awed and inspired, maybe to study science or maybe just to think about their place in the universe. It's a lot of fun. It's very satisfying in terms of communicating things that we're passionate about, the astronomy, the science, the research that we're doing. It's a very important part of our outreach mission.
I think the reason that I really fell in love with astronomy is that it brings a philosophical view of who we are and of how the universe formed that really is missing from any other science.
I sort of view the entire scientific endeavor and where we've gotten to in science. The fact that we can write down simple laws that explain apples falling off trees, to planets orbiting around stars, to galaxies forming and evolving, to how the universe evolves. I consider that one of the greatest achievements of civilization.
Our country was founded by explorers, and that gene for exploration, I think, is just part of humanity.
The largest telescopes that we have these days are really team efforts between not even just different schools across the nation, but even different countries. It's quite a global and shared field. Right now, Yale's in a good place because we're part of some of the big projects, but there's lots of big, large international and collaborative telescopes that are being built, and for Yale to continue to be a strong astronomy department, being a part of those projects is fundamental.
The next generation of telescopes will provide capabilities we've never had, and they will find new things. There's no question about it.
These are the tools that will really allow us to take, the next huge scientific leaps. Not steps, but leaps into understanding the universe and how we humans fit into it.
If If we just stay here on the Earth and only look at the Earth and look down, then we're going to have a very limited view of our universe. We look out, away from the Earth. We look at other stars and other planets and other galaxies. It expands our horizons and tells us what's out there and what is our place in the universe. How did we get here? Are we alone? Those are all big, profound questions that we want to know the answers to. And astronomy is really the only way to do it.